Welcome to Nuclear Matters from the Australian National University College of Systems and Society. I'm your host, Liz Williams, a nuclear physicist and nuclear systems discipline lead for the ANU School of Engineering. Today's episode takes us to Montebello Island, a former UK nuclear weapons test site off the coast of Western Australia. Our guest is Madison Williams-Hoffman, or Maddy for short. Maddy is a postdoctoral fellow at the ARC Radinnovate Industrial Transformation Training Centre at ANU. She uses chemistry to explore how plutonium from the weapons tests carried out in the Montebellos have moved through the marine environment. She's kindly joined us today to talk us through what she's found and help us understand why it matters for our explorations of future uses of nuclear technologies. Let's listen in. Hi, Maddy. Thank you so much for joining us today on Nuclear Matters.
That's okay. Thank you for having me.
I know your work is focused on Montebello Island, so I'm wondering if you can tell us a little bit about the history of Montebello Island, what happened there, and also what it's like now.
The Montebello Islands are an archipelago of around 260 islands and islets. They're limestone based, so calcium carbonate, which is super common among the whole Northwest Shelf. They're historically important because in 1952, the very first nuclear weapon tested on Australian soil occurred there, Operation Hurricane. And then in 1956, there were two other detonations, Operation Mosaic G1 and Operation Mosaic G2. There's a lot of history around these tests aside from the fact that they were atmospheric nuclear weapons tests. They were conducted technically by the United Kingdom with permission from the Australian government. So that's very unique in a political context. And it also means that all of the testing was sort of carried out by another nation. And as a result, we don't have a lot of historical information today about parameters or the background information behind what happened and why. So Operation Hurricane was a 25 kiloton weapon, and kiloton refers to the amount of TNT that you would need to create a explosion of equal size or magnitude. And so for reference, similar in size, but a little bit bigger, I think, than the weapons that were detonated in Nagasaki and Hiroshima. Operation Mosaic G1 was slightly smaller at 15 kiloton, but Operation Mosaic G2, and I was just doing some more reading about this morning actually, because the yield there is disputed, and there's a very long history around it. But the range that people give is between 56 and 98 kiloton. So either way, greater than anything that had come before it. And to date, it's still the largest weapon detonated on Australian soil. Aside from that, some other facts. Operation Hurricane was a ship-based detonation. So essentially they put the weapon in the hull of a Navy frigate and they detonated it from afar. They were trying to have a look at what would be like if someone managed to sneak a nuclear weapon into a populated harbour. So that was the point of that. And the Operation Mosaic G1 and G2 were different in that they were terrestrial tests. So those two weapons were put on top of 30-metre aluminium towers and they were detonated from there. So immediately from the outset, there's a whole bunch of different weapons-related factors, like the size of the yield. Then there's the type of detonation, so what I would sort of call marine versus terrestrial. And then if you get into some of the declassified information, you get a little bit more background on what was actually in the weapons, because all three were, at their core, the fissile material was plutonium. The plutonium that was in Operation Hurricane was, more of a pure fission device. It was very early on in the nuclear weapon testing period. So basically plutonium that they'd gathered, that they'd made in the UK, but also in Canada with a likely uranium tamper. But I say likely because we've yet to find any sort of historical documentation that confirms that.
Yeah.
And then Operation Mosaic G1 and G2 both appear to have had slightly more fusion-related components because as the weapon program developed from 1952 to 1956, obviously there was a start towards more fusion-based hydrogen bomb devices.
Yeah, okay. So 3 events, basically, and the signatures of each of those would be different, yeah?
Yeah, correct. Because the source of the plutonium, at least between Operation Hurricane and the Mosaic tests, would have been quite different just due to the period of time in which the weapons were created.
Right.
There was also quite a bit of a rush during that whole era in order to get these devices up and running and to get the data back. And the UK actually used at least Hurricane to sort of prove that they could have a seat at the table with the US. And there's a whole bunch of other political elements to it on the side. But yeah, it means that the source of the plutonium in the 3 weapons is different, which means that we can potentially use it to sort of differentiate where the plutonium is coming from in the samples that we took at the islands.
What's the reason behind the differences in the plutonium? What is that because of the reactor it was bred in, that kind of thing, and how it was produced? How the reactor was run? Is that?
Yeah, a little bit. It's where and how the plutonium was manufactured and to what grade or quality.
Yeah.
So the smaller, so we use the plutonium-239 to plutonium-240 ratio. That's the one that's most commonly talked about. And there are others, but that's the one we primarily refer to. And the lower that value is, the closer it is to what's called weapons grade.
Yeah.
So basically, you want more 239.
Yeah.
So obviously, the smaller, the better. Another really important factor in what plutonium atom ratio you have is the type of detonation. The more material that is able to go fissile, you have different plutonium ratios as a result of that. So the way that manifests more generally is a higher yield would generally have a higher plutonium-239 to 240 ratio.
Let's go now to your work in and around Montebello Island. I'm curious about the significance of studying plutonium in the marine environment like this. Like, what was known before you started your research, and what drew you to the Montebello site?
What drew me to the site was the fact that I finished my industry placement doing the chemistry, was still really excited, and had to do an honours project. And I thought, okay, here's a nice little stepping stone. The supervisor of that mini project kind of put me onto someone at another institution who just had some samples in the freezer that they'd taken from a field trip a couple of years ago, but hadn't had the time or whatever reason hadn't got to them yet. They sent me those samples.
Okay. What kind of samples were they?
Marine sediment. It doesn't strike a chord with a lot of people, but if you think of the beach or a lake or any body of water, the stuff that sits at the bottom, the seabed, depending on the type of environment or ecosystem that you're in, it can be quite dynamic, or it can move around or be transported quite a lot. Or if you're in quite a stable environment, it can accumulate over time. So it can be a really good way of assessing, for example, legacy contaminants, how the environment has behaved over the past however many years, because it's kind of like a library, can preserve a record of time.
Yeah. Okay. And
this project, it was originally only surface sediment, so the top 10 centimetres. And what was really interesting is that that collaborator, who became one of my PhD supervisors, he had run a couple of plutonium measurements out of the 11 samples. He'd done 3, I think, mainly, again, because the chemistry is really involved. And I just finished a bunch of plutonium chemistry and could apply it quite easily to this new set of samples. From that little set of samples, we're able to get essentially a transect of the region and just be able to finally put some more numbers of how much plutonium is present in these marine sediments, and then compare it to a control site. So that was the honours work.
I think one thing that might be worth just addressing is basically when you do the chemistry, plutonium acts like plutonium. It doesn't matter if it's 239, 240, right? So you're extracting all of the plutonium, at least to the extent that your method can from a given site. And so you were doing that, and you said for a transect, so you're taking a linear, like if you draw a line on a map, you're taking even steps along that line, for instance. Is that how it works?
Yeah, that would be how you design it. In practice, taking samples in the field, especially in the marine environment, is a lot more of a let's just see what we can get type of situation. And the Montebello's can be quite hostile. Yeah, that's a good word. So tough environment to do field work in. So the samples, while they were in a transect, so they were in a line, were spread at different distances in those samples from mainly the Operation Hurricane site. So we had some north and we had some south. Another important factor to mention is that in the marine environment, plutonium is considered to be really particle reactive, which means you release it into a beach, an archipelago, plutonium falls out into the water. It's assumed that a good or great portion of it will actually adhere or adsorb to the particles, the sediment that's sitting at the bottom.
Okay.
So that's why looking at the sediment is really important, because it can over time accumulate or hold on to these anthropogenic radionuclides that are particle reactive.
Okay.
So that's a big reason for looking at plutonium specifically in marine sediment.
Okay, so it kind of traps it, basically.
Yeah, it prefers the company of sediment more than it prefers the company of water.
Okay. And I'm imagining when you're deciding which places along the transect to sample from, I mean, obviously it's not just like this nice wide open field of sediment, right? You're basing that on what's there and whether you think you're going to be able to get a reasonable sample from that spot, right?
Yeah, 100%. Because the region actually has a really big coral population. So coral bommies are, you can't sample on top or around them. There's just no sediment there. It's entirely field dependent. As well, because the archipelago actually is quite shallow. It really depends, honestly, at the time of day that you're there, depending on the tides. So there's so many other different, physical factors at play with like where we were able to sample during that trip, which I wasn't a part of, which was in 2015, but then also our subsequent trip, which was in 2020.
So what did you find?
Yeah, from the initial piece of work, we found plutonium maximum activity concentrations at, I think it was like 2,900 becquerels per kilogram, which is considerably greater than background. Mm-hmm. If we then kind of look into those results further, the sites that we had that were highest in plutonium levels also had what we call radioactive particles. So another factor that can influence how much plutonium you have in any given sample or location is the physical and chemical form that radionuclide was released into the environment. We sort of make this kind of inherent assumption that they're released kind of like as aerosols, and then they filter down and they sit on the water, and then they calmly, nicely attach to the sediment, and they just sit there. And those assumptions used to be made quite regularly in terms of modeling the accumulation over time. What we've actually seen over the past, more so since Fukushima, is this very concentrated effort to study, to actually confirm that. And as part of that work, they found that at most sites that have had some sort of nuclear incident or accident, they've been able to find these heterogeneous clumps or discrete points or particles, really, really elevated activity concentrations. The best example of this is if people have heard of trinitite from the Trinity test in New Mexico. It's like the glass substance that was formed as a result of the super high temperatures of the detonation. And that glass has higher activity concentrations than the rest of the environmental media.
I'm wondering if we can try and put this in context. So it's above background, 2,900 becquerels per kilogram. How much above background are we talking about? And how would that have been dispersed? You're talking about these particles of activity, right? What can you give us a better sense of like what that would be like around the site?
Yeah. So in that honours piece of work, the maximum about 2,900 becquerels per kilogram. Our control site, which was still in the islands, and we know that it was still impacted, so it's not a nice laboratory control. It's an environmental control.
It's hard to get an actual control pre-weapons tests, right?
Yeah, it is. But this background site that we took was about 2 becquerels per kilogram and about 15 kilometres away from any of the detonation sites. Mm-hmm. So that's nearly a couple orders of magnitude different.
Is that if there were humans hanging around this site, would that be a matter of concern from a health perspective or like?
I can't answer that. So we would be able to use these values in a dose assessment. Mm-hmm. But what's really important here is that they're all in marine sediment. Yeah. So in terms of risk to people, and because they're alpha emitters and that alpha particle doesn't travel very far, unless you're sort of rolling around ingesting, inhaling sediment particles inside of your body, it's unlikely to have impact, but that would require, these numbers haven't gone through a human dose assessment. Yeah. So we just kind of have the values, but considering everything else in context, the human risk profile would be quite low.
Okay. Yeah. Alpha particles, you can stop them with a piece of paper. So, you know, I'm just trying to get a sense of like.
Or a wetsuit.
Yeah. In terms of the significance of that, and maybe moving away from humans now to, you know, obviously humans don't exactly spend too much time in such environments. What about the other creatures that would be living nearby or like any of the I guess, seaweed plants? What's the significance of that?
That was sort of the question that spurred the next portion of work, which was the PhD. And in my PhD, we basically went back and we took more surface sediment samples, the same as the honours work. But instead of at 11 locations, we had over 70 in a more systematic grid sort of sampling pattern, because the main aim of that was, okay, we have these levels which are high in certain areas, but there are a smattering. The archipelago is like more than 50,000 hectares. Like it's a huge area. And we had this really small concentrated effort around detonation sites. Mm-hmm. So the first part of that work was, okay, let's just do like pretty much a baseline broad assessment. Like let's figure out, let's take samples not just close to, but north of, south of, through the whole region. Mm-hmm. That was followed by taking sediment cores, which if you can imagine just a piece of like poly pipe, essentially the divers, not me, but the fabulous fieldwork team and marine ecologists, divers went down and hammered these plastic pipes into the seabed to about 1 metre, and then they pulled it up. And then, as I was talking about records and libraries of history in sediment, that's what that part of the project focused on. Was we know what's on the surface, which is kind of, if you think of that's the most recent deposition, that's the most recent sediment there is, it's on the surface. Mm-hmm. The cores were to try and see if we could see any history, if we could make any sense, a bit more of like, if we have the levels, then like, how did they get there? Have they been there the whole time? Have they been held on to in like a really strong, persistent way, or maybe are they being recirculated or regenerated, and all of those different questions. Okay. The last part was that we used that to look at the biota.
Okay. I'm just imagining the divers trying to get this like 1 meter long poly pipe down into the sediment and like getting that sample such that it's not, you know, all getting mushed together. Like, how does that work?
With great difficulty. And the truth is, like, it does get mushed together as you compress anything. It will become that area in which you have sediment becomes smaller, especially like at the bottom of the core. It's more of a problem in areas or environments that have really fine particles because the finer they are, the more they can clump together, the more they can compress. But what they do is after they've hammered in this 1 meter poly pipe, they cap it at the top and it forms a kind of suction so that when they then pull it or yank it out of the seabed, sometimes with the assistance of underwater balloons, depending on how stuck it is and how well they've been able to hammer it in there, and they pull it out and then cap it on the bottom as it comes out.
Okay.
But what you can do is take a measurement in situ after they've finished hammering it, they measure how far the sediment goes down in the core, what it's out on the surface, and then the difference between those two values you can correct for compression.
Okay.
But that makes it sound very a very exact science, but like any field work, it's difficult, especially underwater, fully clothed, because the Montes, aside from being a nuclear legacy testing site, is also known for irukandji and a whole bunch of stingers and stuff. So heavily clothed.
You have to work for your science there.
Yeah, you do. And they all volunteered. Like, I didn't pay them anything to come on that trip. Yeah. If there's anything about marine ecologists, is that they're extremely passionate about the ocean, and no matter what part of the ocean it is. So, yeah, I was super fortunate.
Awesome. Let's go to the biota, though. So how did you go about figuring out the potential impact of plutonium on biota in that environment?
Yeah. The question itself is really important. To think about how we answer it right from the start. Environmental impact assessment or radiological impact assessment can be done in a whole bunch of different ways. Like a lot of contaminated site assessment, you can do a desk-based study, which is where you just kind of get values from different data sets that are published on similar organisms in similar ecosystems, and you can plug that through software, or you can do the calculations by hand. You apply different assumptions, factors in your model in order to get a dose rate at the end.
Yeah.
That's an absorbed dose. And then you compare that to what we call a screening level or a guideline or a threshold, some sort of amount over which you might have some sort of impact, health impact, whether that's in the individual. There's also like population level. It gets very complicated very quickly.
There are factors that relate to how sensitive an organ might be, or how likely it is an organ's gonna or bones are gonna latch onto that particular isotope and have it in a particular part of the body. Like, there are various factors like that go into figuring out how significant a dose is.
I'd just say that for non-human biota, the organ-specific weighting, they call it, because radionuclides are just elements. They're just chemical elements. And like all chemical elements, they have different affinity. They like different organs better. They will accumulate in different areas depending on what element it is. So for example, strontium is really well known to really like bone.
And it has a long half-life, so that's always fun.
Yeah, and cesium is normally more concentrated in muscle tissue. Yeah. And that's to do with ion channels, and it behaves similarly to potassium. That actually doesn't normally happen for biota, or non-human biota, because if you think about the differences in even just organ systems between an ant and an elephant, like, they're incredibly different. Yeah. And there actually isn't a whole lot of, not for lack of trying, but there are so many different species that exist in our world and so many different body systems that information just doesn't exist at a level where we can apply organ-specific weighting to non-human biota dose assessments yet. If you have a specific study, people will go into, if they're looking at a specific species that might be at risk at a near a reprocessing plant, or if you have a specific study, they might do that, but generally it's too complicated. Right. So for the non-human biota, normally we consider them to be an ellipsoid for modeling purposes.
I mean, we do that for humans too. Yeah. It's kind of funny. It's like, look, it's going to be a person-like ellipsoid in this model.
Yep. Small circles, big circles. That's as fancy as it gets.
Okay.
At least in this assessment. Yeah.
Okay. I can imagine it would be very difficult. If you're trying to figure out like whole ecosystem impacts, right? It's not like you're looking at one particular organism. You've got a bunch of different organisms that you're potentially considering. I was reading about this the other day. There's like almost a tendency to go, these organisms don't necessarily live all that long compared to, let's say, humans, or not all of them, but some of them. And in those particular cases, like, thinking about the impacts of natural radioactivity, for example, the exposure time is going to be less. And so there's a tendency to go, well, if it's safe for humans, it's safe for everything. Can you comment on that? Do you feel comfortable commenting on that? Or
I guess it's important to contextualize that in terms of like an ideology. If it's that for a very long time, actually up until 1996, that was in the radiological world in terms of assessment of risk to things from radiation. That was the philosophy. If you've assessed the site, if you've assessed the source and the risk, and people are fine, then everything else should be fine. That's like an underlying flaw, I guess. That's the whole antithesis to science, is assuming something is okay. Yeah.
We always have to test the assumptions.
Yeah. We're not ever really proving anything. We're just constantly disproving. So after 1996, a bunch of international bodies, so UNSCEAR, the ICRP, they're just big international groups that help police, I guess, how people assess risk from radiation to things. They released a bunch of documents that said, okay, well, now we should really consider risk to the environment in its own right. And I think it's important because we as humans have very different biological systems to like algae or seagrass or plants or shrubs or anything. Yeah. And that's actually one of the biggest gaps in the work at Montebello, is that there was a whole series of reports that were done between 1970 and 1990 by the precursor to our PANZA, our now federal regulator. And they're really, really good reports. Yeah. It's really good data. They did a good job of assessing the terrestrial system because that's where people were. Yeah. And that's part of the reason, this ideology of we just need to assess harm to people. We're also, as people, I feel like we're self-inclined, like if you read news articles about clickbait, all of that kind of stuff, the stuff that gets our attention is how might that harm me as myself, as my body. It's the reason why for so long we just knew nothing about the marine environment at Montebello. Right. But if we kind of step outside of that, it's mean to say self-absorbedness. But if we step outside of the lens of just looking at risks to people, which is still super valid, and we need to do it, and we need to make sure that all the data we have is current and validated. Well, we should also be looking at these ecological systems from a moral point of view. They've existed long before humans existed on Earth. And I think there's a moral superiority to the assumption, that if people are okay, then the environment will be okay. We're now starting to put more emphasis and value on looking at environmental systems, not only from a risk perspective, but because if we can look at these anthropogenic radionuclides and look at the different levels in biota, different levels in sediment, can actually help us to better understand those environments that are otherwise really hard to observe. Like if you think about how a fish ecologist might go about observing a group of surgeonfish or whatever in their local environment, like the resources that you need to actually capture that information is a lot. Yeah. Cameras, are you putting someone there? Like you're putting cameras in, someone's got to go collect them, you got to analyze the data. If we can actually kind of use these anthropogenic radionuclides, at least at the Montes, is like, can we use that somehow to better measure these otherwise hard to measure or invisible processes? And that's a bit of a tangent, but I think it's just that assessing environment for risk has value because we are all so different and operate in different ways. But then it also opens this door of opportunity to, once we've assessed risk, then how can we better understand our natural environment by better understanding how these anthropogenic things persist and move through and interact with it.
Mm-hmm. So what kinds of things can you use these anthropogenic signatures to study?
One that is, I think, really interesting, it's to do with provenance of where things come from. Mm-hmm. The Montebellos, if we're talking about plutonium 239 to 240 signature, is extremely low. It's like significantly lower than global fallout in the southern hemisphere. So what you'd find in a background sample, which is like 0.17. The Montes sits anywhere between 0.03 and 0.06, depending on the level of influence. So that's significantly lower. So if you were looking at, for example, whether a certain species of fish migrates through the Montes or maybe has a hatchery or a rookery, or if you're just looking at where things are along the West Australian coastline, that plutonium signature is super distinct. I think they're super exciting to help us, better understand these natural phenomena that are otherwise really hard to measure. Like how do you follow a school of fish around? Like it's impossible. They try and do it with turtles with the loggers on their backs and stuff, but like at some point it becomes pretty expensive.
I'm wondering if we can go back to your work, and I'm curious in particular about how your findings change how we might think about the role that these isotopes like plutonium-239 might play in marine environments.
I think a good way to start that is to think about Australia as like a geological unit. We have really unique ecosystems both on land and in water. Mm-hmm. And we don't have an incredibly good understanding of how anthropogenic radionuclides like plutonium, how they behave in the marine environment over any given period of time. And the Montes provides quite a unique way of looking at that relationship or looking at that environmental behaviour, because aside from the nuclear testing, there is no permanent human population that lives there. There's been no significant anthropogenic activities otherwise. There's been no redevelopment. There hasn't been a lot of input otherwise. It's otherwise untouched. So if we're looking at designing studies or tests, it is actually what we call a really nice natural laboratory. And it's this project, the PhD work at the Montes, has provided a publicly accessible data set that is a really good first glimpse at, if we have a release of plutonium of however much, this is what we can expect to happen in an Australian marine ecosystem and environment. These are levels that you may expect to persist over 70 years. This is how you might expect those levels to change over those past 70 years. This is how we might, for example, we used sedimentology and a little bit of geography and oceanography. Basically, we looked at in the archipelago where sediment was moving over decade-long periods. And we're only able to do that or verify these sediment transport pathways or where the sediment was moving because we had the plutonium values and we could see this gradual, like a gradient in activity, which was able to verify these sediment transport pathways.
Yeah.
If we can do something like that at the Montes, then it helps us in understanding our broader Australian marine environment, but it also shows that we don't have a lot of other information publicly available. It was really actually hard to find comparison sites, which is largely why we decided to do samples along the West Australian coastline to compare to, because it's all well and good to say 2,900, 600 becquerels per kilogram, but to most people that doesn't mean a whole lot. And even in the scientific community, there's no benchmark that says, like, this is how much plutonium you should have in your marine sediment. Like, it's all relative.
Right.
And establishing what's normal for these anthropogenics, I think, is really important going forward. In Australia, considering our new agreements and where we might be going with nuclear in the future.
Yeah.
It's really important to have that strong environmental foundation and understanding of what it looks like today.
Yeah.
Where are levels higher? Why might they be higher? If we're looking at signatures, where are these sources coming from? How are they moving around? Mm-hmm. I think there's incredible value into understanding that from, a baseline point of view. The Monties is interesting because we have nuclear testing there, but also I just think about all of the other Australian coastline, which is likely to be background. But again, assumptions. If you don't know, you don't know. So, and a really important first step in establishing how we do these kinds of assessments at a small scale, which can hopefully be increased and worked on and expanded in future across Australia.
You mentioned specifically the, understanding for an Australian environment and Australian ecosystems. And I'm wondering if you can expand on that a little bit, because we have some listeners from, US, UK. How different are the environments likely to be? What do we need to keep in mind with regards to that in terms of how different do we need to approach this?
For a period when I was looking at my organism data, I had this assumption that I couldn't use the data sets from the Northern Hemisphere because their species would be different to the Southern Hemisphere. And one of my supervisors pointed out that, we actually don't know that. It's the absence of any confirmation or rejection of those similarities or differences. Mm. But the fact is that in our data sets that we use to pull to do risk assessments or dose calculations, most of them in the software that we use globally comes from the Northern Hemisphere. And it's purely because there are more nuclear sites in the Northern Hemisphere. We don't have a nuclear power industry here in Australia, or a lot of places in the Southern Hemisphere or in the Pacific. And if we look at, the Northern Hemisphere, even in the United Kingdom, North America, there are just a greater number of sites that have had some sort of nuclear event.
Yeah.
So it just stands to reason that there is more data of potential impact uptake. Any sort of radiological information is centered around those sites. Mm. It becomes complicated when we think about nuclear weapons testing sites specifically, because there's actually quite a few in this part of the world. Yeah. The Montebellos is just one of them. People know of Maralinga and Emu Field in mainland Australia. But then, of course, there's also the testing at French Polynesia by the French government and the testing at the Marshall Islands by the US. Yeah. And it becomes a question of why we don't have data at these other sites. It's a complicated question to answer, but that's also another benefit to having assessments at sites like the Monties, where we've been fully supported by our federal government here in Australia to do these analyses and assessments, and it's been very politically easy to navigate here in Australia, at the Monties at least, and whether we can apply some of the information that we're collecting from the Montebello site and help maybe apply it or consider it in context with the sites at French Polynesia and the Marshall Islands, which have just by searching publicly available literature, have significantly less modern data available. So I think the broad answer to that is just we don't know the levels of similarities and differences. And I think the reliance of our software modelling on data sets that use Northern Hemisphere site assessments is probably as necessary at the moment because that's what's available. Yeah. But we just don't know if it's similar or different. And I think that not knowing, it means that those assessments are worth doing here in the Southern Hemisphere.
Yeah. But it's important to actually verify that those assumptions are valid, right?
Yeah, and like we do have different species that just don't occur really in or around the nuclear sites in the Northern Hemisphere. For example, in the biota chapter of my work, we took mangrove tissue, not the sediment that the mangroves sit in, there's a lot of work on accumulation of contaminants in mangrove sediment, but in the actual tissue itself. And that's kind of twofold, I've found from looking through literature and finding practically nothing, is that mangroves occur not commonly up in the Northern Hemisphere.
Yeah.
They prefer a warmer climate normally. So that plays into it, but also because they're not commonly considered as part of a conventional food web. They're not like seagrass or seaweeds, which are known primary producers, which get fed on by the small fish, and then the big fish eat the small fish, and then the shark. Mangrove specifically doesn't generally follow that food web trajectory.
Right.
So if you're looking at an accumulation assessment where you're like, okay, we need to measure what's in the things that get eaten, and then we can work our way up to look at biomagnification. Mangroves don't normally form part of that because they get consumed by detritivores. This is getting very technical, but
what are detritivores?
like things like crabs and crustacea that they wait for something to die and decay, and then they will consume that decaying matter. And mangroves showed the highest uptake of plutonium of any of the species that we looked at. And it's super interesting. And then it's like, okay, well, if that's the case, but they're not contributing to the food web, okay, that's probably not a bad thing. But can we measure in a laboratory study, can we use the plutonium uptake to maybe help measure growth or nutrient uptake, or have a better understanding of how the plant growth system works, or how it distributes nutrients or different elements? It just, yeah.
What's the closest chemical analog to plutonium in the natural world? What does it behave like?
Plutonium is a bit of a funny creature in that in the environment, it's very unique in that it can exist in multiple redox states at the same time.
So wait, what's a redox state?
A redox state's to do with like the charge of the plutonium.
Yep.
In practical terms, the redox state can help govern how soluble it is.
Okay. Yep. So how likely it is to get distributed in a body of water, for instance.
It can theoretically exist in a natural environment in, I think like 5 or 6 states, whereas most actinides or heavy ions, heavy elements, they can only exist in 2, 3.
Yeah.
Because there's this greater variety in the number of redox states that it can exist in. It environmentally, it kind of has a little bit of its own category.
Given that Australia is considering enhancing its current engagement with nuclear technologies, and I'm thinking AUKUS and conventionally armed nuclear-powered subs in particular, given that they're going to be in a marine environment, what considerations might we need to make about the potential risks of harm to marine ecosystems if, say, worst-case scenario, an accident happened?
The best value at this point in time in terms of our knowledge of things that could come from a nuclear-powered sub in the event of an accident, which would be obviously very, very unlikely, is we need a strong foundation. We need to know our baseline, and we need investment in developing and sustaining our capabilities to measure those anthropogenic radionuclides, because the measurement, the chemistry and the physics and the detection, everything that goes into generating that number, there's so much work. And in Australia, there's so few people who have that knowledge and have the resources to be able to do that. So it's one, obviously, having a body or program of work, which I know is currently underway, in understanding like what's normal in our marine environment here in Australia. Like it's so important to know what is background, because you can't make a judgment over whether something is increasing or decreasing if you don't have a point of reference.
Yeah.
The second part is making sure that we invest in generating our workforce, our our knowledge economy. I think about other people, the small number of people who are in the same field here in Australia in terms of radioecology and radiochemistry.
Yeah.
And there's no course, like you can't take a course in radiochemistry.
Yeah.
So we need to create those pathways that are a little bit more defined.
Yeah.
They're a little bit more visible.
Yeah.
And that way we're helping make sure that when the current people who are doing the fantastic work of environmental measurement in Australia, when, they're ready to retire, whenever that might be in a couple of decades, that we have the next wave of people to follow through. It's super important. That's part of the work here at ANU in the ITTC is trying to start forming those pathways.
Yeah.
Because it's really hard. It's a bit of a chicken and an egg, like how do you start an undergraduate course if you have if people aren't aware that these professions even exist.
Yeah. Well, this one strikes me as particularly difficult because it's actually quite interdisciplinary. You need to know about ecology, you need to know about environmental science, you need to know about chemistry, you need to know about biology, all of these things.
Yeah. And now as I'm learning electronics and engineering and
finite element analysis and probability calculations, all of the above.
Yeah. And I think to me personally, I get such a kick out of being able to if people ask me what's your job? I just say scientist now because it's just too hard to put a blanket I'm a chemist, I'm a physicist, which always sits funny because I haven't ever taken physics, but I've just learned all of it on the job. And I've learned all of this ecology and fish feeding mechanisms, and it's a privilege of this position to have been able to work so closely with so many different people who are so passionate about wildly different topics, working with a sedimentologist who tries to put my sediment, in his mouth to try and determine grain size, and I have to explain very clearly and very quickly, please don't do that. That's a very bad idea. But also, why are you doing that? What's the point in doing that? And he's explaining that you can sometimes understand the separation between sand and silt by the way that it feels between your teeth.
Kind of a sensor, yeah.
Yeah. And I feel maybe in our undergraduate courses today, I feel definitely when I started that it felt very much like you're a chemist, you're a physicist, you're a biologist. And I know that you can take courses in other things and expand, but just this particular path is you have to walk so many different paths. Yeah. And it's hard. I think that's a really good benefit of the Radinnovate ITTC and these other groups that are starting to form at a postgraduate level is that you take what you learn in your fundamental theory and in your pure streams. And if you're someone who's interested in dipping your toes in pretty much every other discipline there is, I struggle to think of disciplines in which I couldn't use that information or insight. Yeah. There's always applications. So it's exciting that we're starting to create space for that and create pathways forward for it because we're going to need it. It's just anyone, if you're pro, anti-nuclear, wherever you stand, we need this knowledge base and source, and we need this expertise.
Maybe it's worth stating, yes, there's a lot of this that goes into the planning of new facilities and stuff like that, but there's also a lot of this that goes into ensuring that we're holding ourselves to account, making sure that we are doing our job to keep things under control appropriately and making sure that things are safe and making sure our environment's safe. Is there anything that we haven't touched on that you wanted to share with our listeners?
I would just implore anyone who has listened to this, because I found my summer internship through the single last slide of a guest lecture, which I didn't actually go to in person. I watched online, but she put up a slide and it had her contact details on it, and it was if you found this interesting, contact me. And that started my whole career in this space, and it's still going. Like, I did a scary jump from PhD to academic position, which is, I still kind of don't believe it. So it works, and it's such an incredibly rewarding field, both scientifically and morally. Yeah, if any of this resonates with someone and they're like, yeah, that could be cool, I'd really like to hear from them.
All right. We'll make sure that your contact details are in the show notes,
yeah.
right?
It feels I feel like a shameless plug, but
that's all good.
We're talking about, not having pathways yet and just trying to start and opening that. It's cool. It's very cool science, and it's very worthwhile.
That's a very nice place to end. Thank you so much for joining me today, Maddy.
That's okay. Thanks for having me.
Nuclear Matters is a production of the Australian National University College of Systems and Society. We acknowledge the traditional owners of the lands on which this podcast is being recorded on or listened to, and pay our respects to their elders and all First Nations people. If you liked what you heard today, please share this episode with friends, family, and colleagues. If you want to send us some feedback on an episode, please email us at nuclearmatterspodcast@anu.edu.au. Keep in mind that this podcast is intended for information and education only. The views and opinions expressed in each episode are those of the individual speakers and do not represent the official policy or position of the Australian National University College of Systems and Society or the university as a whole.